Let's see, right now we're in the process of studying factorization. And we left off last time with this definition, unique factorization domain. So UFD, right, let me just remind you, a unique factorization domain, it's an integral domain. So let's say an integral domain capital D, where each non-zero non-unit, say little a in capital D, can be expressed as a product A equals P1 dot 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 P sub K, where each P sub I in D is irreducible. Okay, so that's what we're looking for when we talk about factorization, right? We want to take an arbitrary element that's not zero, not a unit, express it as a product of sort of the basic objects in the set, right? So we're sort of trying to generalize the idea, right? First of all, in the integers, right, every positive integer, or integer greater than 1, can be expressed as a product of prime, so those play the role of irreducibles in the integers. And then also in f bracket x, right, we showed that every polynomial of degree greater than or equal to 1 can be expressed as a product of irreducible polynomials. In both of these situations, there's a uniqueness that goes along with this, right? So I haven't finished my characterization here, where each P is irreducible. And then, moreover, this factorization is, well, it's not quite unique, but it's unique up to reordering, right? So, swirling around these irreducibles here, and associates. Remember, two elements are associates if one is a unit times the other, right? And so, by inserting units or sliding units around, right, we consider that sort of trivial manipulation, right? So, the next question you might ask is, all right, let's say that we've got an integral domain D. How would we know whether we're in a UFD or not, right? So what we need, I mean, that could be a difficult question. So what we'd like to do is get some conditions, and that's what we're going to build up towards, is we'd like to build or identify properties of D that guarantee that we have unique factorization. All right, so that's where we're headed. It'll take some work, right? But we'll get there not too long. Okay, so let's start off with the definition. So a family of ideals of some ring of the form. So let's say that we have ideals, and it's going to go I sub 1 contained in I sub 2 contained in I sub 3, going on forever, potentially going on forever. We call this an ascending chain of ideals. So this is an ascending chain of ideals. Fine. So our first result from this chapter, I'm going to call this lemma 45.1. So let's let R be commutative. So let's let R be commutative. So if we have an ascending chain, so if I1 contained in I2, contained in I3, contained in ... is an ascending chain of ideals, then it turns out that the union is an ideal. So then I, capital I, which equals the union I equals 1 to infinity of I sub I. Let's use an n rather than I here for our index. So n equals 1 to n is an ideal. And the proof is straightforward. We're just going to use the ideal test. Of course, it's non-empty, right? Each of the i's, the capital I's, is non-empty, so its union is going to be non-empty. So for the proof, since each I sub n is non-empty, we have that the union, capital I, is non-empty. So now let's let let say A and B be in capital I and little r be in capital R. So I'm just going to run the ideal test. Capital A, or sorry, little a is in capital I, which means that it has to be, right, this is a union, and so it's got to be in some I sub n, or let's say I sub m. Same thing, B has to be inside some I sub n, right? So, so then there exists, say, little m and little n, right, natural numbers, such that A is in I sub m and B is in I sub n. Okay, so now let's think about what we have. We have this ascending chain, right? So let's say that A is in I sub 5 and B is in I sub 12. Well, since I sub 5 is contained inside I sub 12, right? They're both contained inside I sub 12. So the point is, because we have this ascending condition right here, we know that both A and B are going to be contained in some I sub whatever, right? Whichever one's bigger, right? So I'm just going to assume it doesn't matter. I'm going to assume without loss of generality that n is greater than or equal to m. So assume without loss of generality that I don't know what I just said, m is less than or equal to n. It doesn't matter. Then A and B are both inside the larger one. So A and B are both inside I sub n. We know that I sub n is closed under subtraction. We know it's closed under external multiplication. So it follows that A minus B is an element of I sub n, which is contained in capital I, and R times A is an element of I sub n, which is contained in I. So by the ideal test, capital I is an ideal of capital R. Right, so nothing earth-shattering there. The whole point is just to recognize if you live in one of them, you live in all the rest of them forever and after, forever and ever. Okay, so we have this idea of ascending chains. So now let's start with the commutative ring. So let's let R be a commutative ring. The ascending chain condition, which is usually abbreviated ACC, holds in R if for every ascending chain of ideals, I1 contained in I2 contained in I3, presumably going on forever, there exists some natural number, let's call it capital N, such that if little n is greater than or equal to capital N, then I sub little n is equal to I sub capital N. So here's the idea. Let me just kind of draw the, well, not draw the picture, but it goes like this. So if you have an ascending chain and you're in a ring that satisfies the ascending chain condition, then what that means is, right, I mean, let's say, eventually what your chain looks like is I sub n contained in I sub n contained in I sub n. So it cannot increase indefinitely, right? At some point, the chain basically terminates and then repeats itself forever after. Another way to say it is that, so here's an alternative way to think of this. So alternatively, R has the ACC if every strictly increasing chain of ideals is finite. When I say strictly increasing, meaning that you have proper containment, right? At some point then, if you continue to have proper containment, then it has to stop, right? You can't go on forever having proper containment. A piece of terminology, I guess. We define the ascending chain condition in a commutative ring if you happen to be in an integral domain. So an integral domain that has the ascending chain condition is called a Noetherian domain. So an integral domain that has the ascending chain condition is called a Noetherian domain. It's after a famous, one of the people who helped develop ring theory, right, named after Emmy Noether. Okay, so this is kind of a peculiar condition. And so our next result gives us a little inkling of why, well, not why, but when you might have this case, right? So it's not clear why we might care about this ascending chain condition yet, although we will see. But at least this next lemma is going to tell us when we're guaranteed that it happens. So 45.2, if D is a principal ideal domain, then D has the ascending chain condition. Or another way to say this is that PIDs are Noetherian. Let's put that in quotes. Oh, PIDs are Noetherian. And so for the proof, okay, so let's start off with an ascending chain. So let's let I1 contain an I2 contain an I3, blah, 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 B, and ascending chain of ideals. Now, one thing we know by our previous lemma is that the union of these ideals is an ideal. So by lemma 45.1, and let's call it capital I, right? Capital I, which is the union n equals 1 to infinity of I sub n, is an ideal of capital D. Fine. But right, we're in a principal ideal domain, which means that I has a generator, which let's call it little a. So since D is a PID, there exists little a in capital D such that the ideal generated by little a is equal to capital I. All right, now little a lives inside capital I, and I is the union, which means that little a has to live in an I sub n for some choice of n. So since little a is in capital I, which I'll write as the union, so n equal 1 to infinity I sub n, there exists say capital N such that A is an element of I sub capital N. So now, if little n is greater than or equal to capital N, we have, so let's see, how do I want to write this? Okay, so I, that's equal to the ideal generated by A. Little a is in I sub n, so this has to be contained in I sub capital N, which is contained in, so n is greater, so that would have to go like this, right? I sub capital N is contained in I sub little n. And then, but I sub n is part of this unions, right? So that's contained in capital I. So look at now, I've got I on both the left and the right hand side, and so that tells us that everything has to be equal, right? In particular, I sub capital N has to equal I sub little n. We can say, and so I sub capital N equals I sub little n. Right? And so what we have then is that this chain of ideals has the ascending chain condition, and so, or I should say this better, this ascending chain right here is constant after a while. It goes I sub capital N going on forever, which means that capital D has the ascending chain condition, which means, which means we're done. A couple of things that I just want to write these down as observations. So the first one, and I think I kind of outlined this before, but let's just write it down now once and for all. So when we say that the ideal generated by A, or when we know that the ideal generated by A is contained in the ideal generated by B, what that means is, right, I mean, this is going to be true if and only if A is an element of the ideal generated by B. Which is true, right? This means, so this is if and only if A is equal to, say, B, C for some B in whatever ring we're working in, right? If and only if, so what does this mean? If and only if B divides A. So here's a sort of characterization, right? Containment of ideals, I think I did say this last time, containment of ideals is equivalent to divisibility, right, in a ring. And that's really, I mean, in some sense, I mean, you want to be able to go back and forth between these, but in a way that's kind of the point, right? We're trying to get a notion of what it means to divide, what it means to factor, and so on. And so what this tells us is that we can characterize it very precisely in terms of ideal generated by a particular element, which might tell you then, PIDs might be an important place to work because all the ideals look like this. In the reverse direction, or not in the reverse direction, not reverse, sorry. So the second observation is, what does it mean for the two ideals to be equal to each other? So the ideal generated by A equal to the ideal generated by B. This is true if and only if both A divides B and B divides A. Which is true if and only if, so let's see, that would be B, use the right letters here. Oh, whoops, yeah, A divides, well, B equals, I just want to use the letters I use here. B equals AD and A equals BC, right, for some choices of A and, or B and C. Now, this is true if and only if, so I'm going to substitute now. So this is true if and only if, what do I want to do? Let's solve for B. So I'm going to substitute this equation into this equation. So we get if and only if B equals B, C, D. Now what does that mean? Well, we've got cancellation, right? All right, all of this stuff, all the work that we're doing here, and maybe I should have said, assume that we're in an integral domain, right? But cancellation tells us then that CD equals 1. So maybe up here I probably should have said in an integral domain. Cancellation, so that means if and only if C and D are units. So what does that tell us? It tells us either one of these equations right here tells us that A and B are associates. So this is if and only if A and B are associates. All right, so now, remember, associate just means that one is a unit multiple of the other. Okay, so what does that mean then? Or what does that tell us? Or how do we... what I'm saying here. So what can we get from this? All right, so equality of these ideals is equivalent, right, to A and B being associates. Meaning you're only going to get equal ideals in an integral domain if and only if we have associates. I think I'm going to stop here. We got some hard work coming up. Yeah, so I'm going to stop here and we'll pick up with this. So we sort of set the stage now to start getting into and understanding the ideas of factorization and when it occurs, when we can do factorization, and in particular, when we're in a unique factorization domain. All right, so we'll see you next time.